Okay, so I used to work in the Corp infrastructure group in the Sydney office at Google, and we manage open source applications in the Corp environment. So all of your standard applications, bind, LDAP, NTPD, what else? Rsync, DHCPD, and so on and so forth. So obviously we want to monitor these things so that we know that they're performing to some acceptable level. The kind of things we care about is not just whether or not it's responding to traffic, but also how many queries are they doing, and are they reporting any errors at the time? We ask our old friend Tom Cruise to give us a hand. At Google, we have this big proprietary monitoring system, and it's proprietary and in-house because it's very well integrated into all of the code that's written there. So you basically, for free, every time you write any code, you just export some data, and then almost magically, it ends up in the big cloud of monitoring. So we wanted to integrate with that as much as possible because it's quite a powerful framework, and it solves a lot of problems in a fairly elegant way, and it scales really well. So we wanted to reuse it. It works it's a white box monitoring system, so the applications give as much information as they can, as opposed to a black box where, say, Nagios checks, probe a thing, and then figure out if it's succeeding or failing, because you have no internal state, or no knowledge of the internal state of the system. The white box test, on the other hand, white box monitoring, on the other hand, is where you actually get to inspect the internal state of the application. So you get to know how many queries it served and how many errors it's currently having or has had so far. It turns out that most applications in open source do give this stuff away as well. So you can query things and ask it what's going on. You can ask MySQL for some stuff. You can ask Apache for stuff. You can ask LDAP for stuff. And LDAP will give you a big dump in LDIF format of all the kinds of internal things. LDAP is actually quite verbose and very useful. But the problem with all of these things is that we need to have a specific tool written to parse each of these formats, and that's a lot of work. So we're like, why can't we come up with a nice general solution for this problem? And it turns out that all of these applications happen to also write a lot of this stuff to their logs. So why not just look at text files that are being written to all the time, take the data that we care out of them, and export that. So the tool then is called mtail for exporting modular tail. It does that. If you were in Junior's talk yesterday in the programming mini-conf, you may have seen this construct before. It's exponential time, which is quite awesome. Big O notation. So anyway, mtail is a modular tail, so it takes modules or plugins, and a plugin or a module is just a little program that says, upon this event, do some action. And typically it's just, as you saw in the previous one, match a regex, and if the regex does match, then do some work. The work typically is counting things, adding things together, extracting a string perhaps, things that you do with regexes. And then we export them over the common protocol. The Google one exports into the Google proprietary one. The open source one, which technically is open source, but not technically because you can't download it yet, is JSON format. So this is what it looks like. Every time we get a metric, sorry, I think I skipped ahead a bit there, maybe a little a leap of faith. So we define this thing called a metric, and it's a thing, right? So a number of queries perhaps for a particular server. So we say a metric is a number of queries, or another metric is a number of errors, and we want to know what the value is. So it's basically a measurement, and we want to know things like when it happened, and a bunch of perhaps other stuff that we want to apply to that. So here's a structure that describes all this stuff. A name to identify what you're looking at, the value it was, and at the time it had that value. And then a type that lets you decide whether or not it's a permanently incrementing counter or it's a gauge. Now the difference between these two, if you're familiar with SNMP, you've probably seen these before. A gauge can change up and down like you would see on a dashboard, and the counter is only going to ever increment. These have very different properties, which you'll discover if you want to start aggregating or performing mathematical operations on these. For example, it's very difficult to take the rate of a gauge, but it's very easy to take the rate of a counter. And so you can see the rate of things over time with counters. But gauges, on the other hand, it's very easy to take averages of them and to sum them up and get an overall look at a cluster of things exporting similar types of data. Of course, the units are very important when you're measuring things because it's important to compare things in the same units, and you don't want to, for example, bits and bytes is, I'm sure everyone's familiar with conversions and confusion arising from that, and possibly you want to store some extra data, so there's a tag thing that maps key value pairs together, which might come in useful if you need to, say, aggregate a bunch of stuff together by the service name that they're providing, but not then throw away the host name. You might want to say, give me all the things in a particular, with a particular tag of, say, a data center name, and then add them together. So I think I covered this. Data is exported over an HTTP server using JSON or CSV. They're easy to parse, as Chris said in the last talk. So the important point about MTail is that it's not actually doing any time series storage. All it's doing is exporting the very point in, like the most recent time events happened, what the value was at that point. The job of collecting this for long term is somebody else's job. So here's a bunch of things that you might use. Cacti, collectd, OpenTSDB, all of them are capable of storing values over time. So this new version of MTail is written in Go because I thought, hey, I want to learn Go, and now I have two problems. And the first one is that I have to rewrite and discover all the original problems I had when I was writing the first time. So yeah, the old one was Python, which is quite nifty. It was very easy to write the plugins because Python is a very introspective language. You can monkey patch things all over the place. So you could just load the Python plugins into the runtime and merrily continue. But the new one is in Go, and it would be at this URL had I figured out how to push to a Git repo in the 5 minutes before the talk. But stay tuned to then. I promise it will be up by the end of the day, definitely sooner. Anyway, it's a re-implementation from scratch, and I throw away a bunch of obsolete craft in the process, which is actually quite good. There's a bunch of stuff that the Python version does have that this one doesn't. The regular expression library in Go right now doesn't fully match the RE2 API. If you've used the RE2 API, it's quite powerful. It does all kinds of crazy things. It lets you look at the named capture groups in a regular expression, so you can refer back to them. It lets you build the filtered RE2 set, so you can match multiple regular expressions at the same time. Sorry, the set gives you the multiple regular expressions at the same time, and filtered RE2 allows you to pick and choose which regular expressions you think are likely to match in a set. So we can use a little technique to extract little atoms out of a set of regular expressions, little bits of text, and then we can do a very quick fgrep-like search over the input, and if any of those little atoms do match, then it's likely that the regex might match, but if they don't match at all, then we know for sure that a particular expression is never going to match. The Python one has this feature and is actually quite fast because of it. Reading from Unix sockets is probably a good idea because syslog likes to log things to that, save disk space. Anyway, let's talk about MTail. The language is very simple. It looks like awk. It's got a pattern action, kind of an action, no, pattern action syntax. As you can see, this one matches new lines and then increments a variable called line count. I just realized there's a typo there. The double quotes are not required. But yeah, that's much of a muchness. Here's a different example. This one matches foo, and then if that matches, it runs a bunch of other regular expressions. If bar matches, then the bar counter is incremented. If the baz one matches, then baz, so on and so forth. Foo is always incremented if foo matches. Did I skip over one? Oh, I thought I had another slide. Pardon me for just a moment. There's a little bit of extra syntactic sugar for parsing. Yeah, you know what? I didn't reload this page before. Sorry about that, little technical issue. Da, 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 da. Yeah, okay. Da, da, da. Some stuff. All right, yeah, okay. Hey, I did fix it, awesome. So it's actually a function. If you match a new line, then now we can add a little label. We've got a key value pair, say label foo bar. Actually, I think that's a typo too. I probably need a parentheses and a comma in there. And then increment line count. And so what actually gets exported, this is an example of the CSV export. The name, the value is a float64 timestamp, arbitrary format. Maybe we'll export it as a UN64 instead. This tells you what type it is. It's currently a counter, gauge is 1. This is a units. I don't know what the units are, so. And then you can see we've set a label, foo equals bar. So now we can search later and say, give me all the things where foo equals bar. And we go, oh, here's one. Capture groups. As I was saying, RE2 supports finding out what the capture group is. The Go one lets you specify them, but doesn't let you refer to them by name, which kind of defeats the purpose. So the second one here, where we can just refer to $3, does currently work. So, you know, we set some labels based on the value stored in our regular expression, and then increment a counter. Timestamps, there's a strip time. I've just discovered that Go's time parsing code doesn't support the C-strip time standard. It uses a completely different thing, so this is completely invalid. It looks more like you just give it a timestamp and it goes and figures out from what the timestamp looks like. So you would say 2002/01 something something hour minute second as the actual string. So basically you look at your log file and go, that looks like the timestamp I want, copy, paste, and you're done. So anyway, in this example, what we do is we take the $date out of the regex, whatever matches, and then parse it with that string. But obviously, like I just said, a completely different string. And then, oh yeah, we do that guy. So example time. This literally only just started working. So, uh-oh, now I'm confused. What I'm going to do instead is turn off the multi-screen, show you what I'm looking at. Yeah, keep that. Oops. And I'm not going to show you it in my Emacs because the font's way too small for you to see. So, can you see the screen? Is the text readable? Okay. I think we need to GDB it. All right, enter logs temp foo progs line count. So it reads files in a directory. There's a program in there called linecount.em. Linecount is a program. So.
Can you move the terminal across a bit?
Oh, yeah. Sorry, it's full size and it's just popped the edge, just a bit to the edge. Okay. Is that better? Not quite perfect. There. Now we're golden. Yeah, you go away. Right. It's not running anymore. Come on. There. You can tell this is live. Really? All right, GDB was just keeping it running. Yes, okay. Where's the example? All right, so line count is exported. Oh, yep, sorry. It's actually a clever ruse of mine to fill in all the available time. Okay, so you can see we have a variable being exported. That's interesting. Okay, now for my next trick. Construct some log data. There we can see that. It's just catting, appending to a file, which is really what logging does. So bam, we go back to this guy. It's spewed out a lot of code. This is all debugging stuff at the moment. Damn it. Reload, 173 lines, yay. Timestamp code is broken. But there you go, see, live example, some actual code. And just to, what? $170 lines, okay? All right, so let's run it with a, why does that happen? Different program. Here's a new fancier one with a whole bunch of design notes in it. This one again matches, stop doing that. Right. We match the empty string, the new lines again, incrementing the line count total variable. And then we've got another one where if there's a bunch of digits or a dot or a dash or a colon or a space, then match that and try and parse it with this little, this is what the Go format strip time thing looks like. Months, underscore means might be a space there, might not be, and then a time format thing. So the file I'm pumping through just has this at the start of it. So that sets, in theory, it obviously didn't work because the output was showing 0 time. That sets the time register to whatever happened to parse, and then we increment foo counter, and in theory, what would happen is foo will then have that timestamp that's just been parsed. I've commented this guy here because I haven't actually supported the increment by support yet, but you can see that you might want to parse out a digit and say that's an interesting count of things. that needs to be added onto a counter. So we can run this guy. Get some stuff happened in the background. And then you see this is a different program now. It still counted the number of lines. Foo never got modified because nothing actually matches caret foo as per that program. Right. So that's some examples. It doesn't get much more complicated than that because just about everything you want to do is either setting a label or parsing a timestamp or incrementing a counter. And you can see you can refer to the stuff that you've parsed out of the log files in order to figure out what variable names or attributes or so on and so forth that you want to monitor. So I also want to show you how it actually works. The program compiles down to a little bytecode and looks... Fortunately, I have that already open. Okay, so if you're not familiar with Go, it looks a lot like C, and it's a little bit more concise. You don't have to type as many things twice as you used to with C, so it's quite good. Anyway, so here's the start of it. We've got a bunch of opcodes: match, jump, no match, increment, strip time, label, ret, push, capref, and load. Inc, strip time, and label are the commands you've seen in the code. They basically do that behind the scenes. Ret returns success or failure of the actual program, and the push and capref and load are just internal references. Pushes onto the stack. Capref and load refer to either string constants or capture groups in the as the parse happens. So we have a little instruction. It's got an opcode and operand. And you can print it with the string function there. And then we have this thread of execution with a program counter and a bunch of registers. And the great thing about writing a virtual machine is that you can make the registers anything you like. They don't have to be little a word. So we have an int. We've got whatever the last match happened to actually return. So this is a list of all the capture groups. So I just realized terribly named. Whatever the last time that was strip timed, and the currently set labels in the current scope. So now a virtual machine is a list of instructions, is the program. A bunch of regular expressions. And so this is, think of it like an ELF format, heavily simplified. There's obviously a text segment where the program actually lives, and then there's a bunch of data. So we've got a regular expression, bit, a string bit, and then some stack allocated. Probably doesn't need to be in that guide at all, the stack. But you can see that there's data segment. So the load instruction refers to stuff out of the string guy, and the match instruction will refer to stuff in the regular expression object. Stack functions, pushing and popping. And here we go. This is how the program runs. So we create a new thread. In theory, this might be able to be pseudo multi-threaded, at least run multiple threads of execution in parallel, using the technique that Thompson wrote about way back. So anyway, we run the, because we're actually consuming a whole line of inputs here and using the a different regular expression engine to perform the match, there's no point in actually trying to consume one character at a time and then possibly fork. But as you saw earlier with the nested regular expression part, it might be potentially desirable to, once you go into a scope and notice that there are multiple regular expressions about to match, fork off multiple threads and go match that one, match that one, match that one, whichever one happens to parse, continue, and whichever thread doesn't, then terminate. So this is the fetch execute cycle, get the next thing, and if it's past the end of the program, then terminate. And switch. So match instructions, what it does is matches a regular expression against the input. And if it matches, then it sets the return register. The jump no match inspects the return register and decides whether or not we should jump past the scope. So we can, here's an example. So if we're looking at the bar regex right now and it doesn't match, obviously we don't want to go into the scope there and increment bar, we want to jump over to the BAS instruction. So increment obviously increments a counter, it gets the reference to the particular counter that we want to increment off the stack, and then increments it. And if the time is, the current time register has a value, then it is set. And if it's not a value, then it's also set. So that's probably what's breaking the that other time code right now. Strip time, obviously, this is the this is what strip time looks like in Go. Anyway, we've got two things on the stack, pop them off, pass them into the actual implementation, and then set the time. Labels, again, pop the key and the value off, and set them. Cap ref, so we want to, notice earlier in the, sorry, scroll up, notice earlier in here, on this line, we set T matches, so the current threads matches are now set to the result of this expression, which is the set of capture groups in the input. And just by way of example, you can see that here, what that would mean is that the that big date blob, well, let me show you the actual capture group one. What that means is the first one will be in the first element of the list, the second one will be the second, and so on and so forth. So when we receive a cap ref instruction, look up that cap reference in the list of matches and push it onto the stack. Load does a similar thing, but we don't have to do any lookup. We've already got the list of static strings from the compiler. So we just look that up and push that on the stack. Return returns. Success or not. And push obviously just pushes some stuff onto the stack. Increment the program counter at the end is always useful. So yeah, that's pretty much it. The compiler itself runs very, well, it's not similar at all, but it has a similar structure because as it's building these structures, we want to keep them around and then pass them into the virtual machine. Does that make sense for everyone? Because I don't think it's worth talking about. It's just a standard Yak style parser. The visitor itself just walks down the syntax tree and does stuff like when we compile a regular expression, we push that into the list of regular expressions, and then the match instruction that gets emitted to the program is obviously match, and then the reference to the end of the list where the new regular expression happens to be. Same for the visit string function, puts the string into the string storage and then puts on a load instruction. Conditionals, never mind. IDs are a little bit different because we're now referring to variables that we actually want to export. Obviously you don't want to export them multiple times, but you do want to be able to refer to them multiple times in your code. So just check if it exists. If not, build it. Otherwise, refer to the one you've already built. And the built-in functions, walk the children first, so they can push whatever they need onto the stack, and then call the built-in itself. The start function is, sorry about that. No, you can't hear me now. Yes, you can. The start function receives lines off this channel that the log watcher code is emitting. So I should probably show you how the logs actually get into the virtual machine. So we have a method watch. and that's just uses iNotify to receive log events. To receive notify events when the log file changes itself, and if an event does happen, we pop the name of the file that changed onto this channel. Then the tailor itself, which is an intermediary, it receives changes on this channel down the bottom here, and every time there is a change, it calls handle log change, which is this function here. Just reads from wherever the current file position is to the end of file, and then parses each line. Sorry, it doesn't parse, it just reads lines. Once it hits a new line, it sends that off to the to that channel. And then, the virtual machine picks them up here and then runs the engine over it. So when we increment things, this metrics thing contains all the actual metrics. So we can pop down to the main function and see handle CSV, for example. It looks over the list of currently exported metrics, turns them into a list of strings, which the CSV writer reads and then dumps out as CSV format. And that's really it. Very simple, but a little bit more powerful than just tail and grep. All right, so time for questions. Yes?
You mentioned before that a lot of the stuff you're pulling data from already has lots of different ways of getting the data.
I'll repeat the question so you don't have to.
Yeah. Why look through the log files when there's already data there and you have to write modules to pass the log files?
Because this is now we have this tool, it's general purpose, and the cost of setting up each new application is a lot lower than having to write something that will parse each of the output. Also, it was a lot of fun. Sorry, I didn't repeat the question, but although I meant to.
My question was, why reinvent the wheel on a log? Why reinvent the wheel on a log parser? When, CollectD's got one, I assume other tools have got them.
Well, we don't use CollectD internally, so the tool didn't exist to export into our monitoring system. Also, it's Google. We're all about not invented here. No, I need a laugh from the Googlers. Yes, Michael?
In Jamie's defence, this is also a rewrite of my bad code from 2007. So, this is an ongoing thing. It became a thing they did, and it was the design pattern that was followed.
Rewrite all Michael's bad code.
Yes.
Down the front? Yeah, you again?
And I guess in the answer is probably not invented here, but SNMP is already about transporting exactly those values as you identified.
Okay, SNMP is an interesting beast. The ASN thing is interesting. MIBs are interesting. The fact that they use UDP as a transport is also interesting.
So I actually had a question about the step after MTEL. I know you're using Google's proprietary monitoring internally. Do you have any idea of what a suitable repository for this information would be being parsed?
Well, I mentioned a couple earlier for time series database. Things like CollectD or OpenTSDB, I've never actually used because I live in the vacuum of Google and so I have no opportunity to use these things. I believe, are perfectly acceptable time series database, but what happens internally is that data goes into a time series database, and that's basically it. Everything that happens from then on is actions on the TSDB itself, rather than like, so contrast with Nagios, which does the checks actively at scrape time. We don't do it that way, so.
Have you done any benchmarking of it and seen how it compares against
I have, and I foolishly forgot to include any of the information on the slides. Obviously, the one I've just finished writing hasn't been benchmarked yet, and I know that it's probably going to have poorer performance than the one we use internally because we're using an inefficient matching technique. The one we used internally used to use a similar method where it would just match each regex as it came to them. We did have a short circuit that would decide whether or not the plugin was even going to attempt to match. So, for example, our team used to run, well, they still do, I used to run an MTEL instance with 4 or 5 plugin handlers for various things, all pointing at all the log files in the system. So we'd have the DHCP and an rsync and an NTP one all running in parallel in a single instance. And so often you would get log lines that you're never even going to be interested in. So you could say, well, I'm not interested in that log file ever, so don't send it to me. This still had fairly bad performance, but Paul over here spent some time investigating. He was the one who came up with the filtered RE2 approach, where we'd test before attempting to match in a more cheaper fashion. Correct me if I'm wrong, but it was something like a 3-time speed up for the first implementation. And then we managed to get somewhere like 10 times as fast. No, actually, somewhere in the ballpark of 10 to 30 times as fast, but towards the end.
Final line rate was over 9,000.
It's over 9,000. Yes. Yeah, so we originally had a parse rate of roughly 30 to 60 lines a second on a particular grunty box, and that's pretty atrocious. After Paul had finished, we were doing 10,000 lines a second on the same machine, which is quite impressive optimization, I think. And then we had another bug, which was the metric storage itself was actually ON to search, and that was chewing CPU time. So we were like, why is the CPU pegged at 99% all the time? And this went on for about a year, and eventually profiling was like, oh, it turns out the engine is actually really fast, and then we should stop optimizing that. We should just make the variable storage a little bit more efficient. And then CPU load dropped down to negligible with, what was it, 3 lines of code? And a monkey patch? Yeah. Does that answer the question? I do plan on running all of these same regression and benchmarking tests on this code, and then doing some publishing some stats. Sorry, can you say again?
Have you compared to Orc?
No, I haven't. But from what I know of Orc's implementation, I think they'll be pretty close. But yeah, that's a good point, very interesting. I don't know if you can get Orc to export things in JSON though. Or you probably could, couldn't you? I'd like to see you write a web server in Orc.
It'd be non-maintainable.
Anyone else?
All right, we might wrap up in that case.
All right, thank you very much. Hope it's useful. Stay tuned to that website if you're interested in actually having a look at the code yourself, and it will be available by the end of today. I'm going to hack on it in, I don't know, the next talk and figure out how to use Git. Yeah.
And on behalf of Linux Australia, I would like to thank you for your talk by presenting you with this gift.
Thank you very much.
Thank you.